Stage 4 of the system development lifecycle represents the moment theoretical IT planning meets the friction of real-world clinical operations. Consider the deployment at Home Health of America. Seeking a rapid transition, the CEO mandated a big bang strategy, scheduling the system-wide cutover for a Monday, the organization's highest volume day for patient visits. The point-of-care failures began immediately. Core software functions failed to initialize, cellular connections dropped as staff accessed records, and clinical documentation stalled. This technical instability created an operational crisis. Staff incurred double the projected overtime attempting to use the system, yet 3 patients were missed entirely. Ultimately, the organization was forced to abandon the software and revert to a paper-based system while the errors were addressed. A successful go-live functions as a high-risk operational pivot, one that demands flawless execution across every preceding phase of the project. This diagram in Figure 5.1 outlines the 12 essential steps of information system implementation. These stages form a strict dependency graph, where the completion of foundational elements is a prerequisite for moving to subsequent phases. Physical site preparation serves as the primary bottleneck. Software cannot be installed or configured until the facility possesses the necessary electrical outlets, data center infrastructure, and server hardware. While the physical buildup is sequential, other tasks run concurrently. The project team must manage digital milestones like interface design and data conversion at the same time they handle the psychological preparation of the staff. A failure on launch day is rarely an isolated software bug. It is typically a failure of the architectural dependencies built during these preceding 11 steps. The first implementation vector is data architecture. Because no information system operates in a vacuum, launch requires the migration of legacy data. Table 5.1 summarizes data conversion parameters, mapping historical fields to new formatting logic. For example, converting a 9-digit health record number to a 12-digit field requires the program to explicitly append 3 leading zeros to every historical patient record. Beyond simple formatting, conversion involves the logical reclassification of patient types and clinical services to fit a new organizational hierarchy. Figure 5.4 demonstrates how these relationships are mapped. If an existing record identifies an attending physician as a gynecologist, the system may need to utilize that data point to logically reassign the patient from a general surgical category to a specific gynecology service branch. Without precise and tested conversion logic, the new system will inherit and compound the data errors of the legacy system. A system's output quality depends on the accuracy of the data entered by its human operators. User interface design serves as a primary tool for reducing cognitive load and preventing user-induced errors. This example of poor design in Figure 5.3 lacks a descriptive title and uses an illogical sequence of data fields. These flaws force the user to hunt for information, increasing the likelihood of input mistakes. Contrast that with Figure 5.2. This demographic entry screen utilizes standardized terminology and a logical left-to-right, top-to-bottom reading flow that facilitates rapid, accurate data entry. Elements like reverse video or high-contrast colors are used sparingly, reserved specifically to draw attention to critical alerts, such as patient allergies. A new interface often requires workflow reengineering. This involves evaluating and changing manual tasks to ensure that legacy habits do not create bottlenecks within the new digital process. Aligning the interface design with a re-engineered workflow ensures the system supports clinical efficiency. The final vector before launch is the dual process of system verification and human behavioral training. Training must be grounded in adult learning principles, focusing on immediate clinical relevance. For example, a nurse should be trained on specific medication entry tasks rather than generic software navigation. System testing operates in a cyclical loop: identify errors, implement fixes, and retest to prevent breaking other modules. Integration testing ensures hardware like barcode scanners communicate seamlessly. Lastly, volume testing simulates peak loads, verifying the network handles mass concurrent usage without crashing. Cyclical testing and targeted training provide the necessary technical and human resilience required for deployment. Once infrastructure, data mapping, and testing are complete, leadership must select a go-live execution model. The rollout models are phased, modules added gradually, pilot, a single unit adopts first, and Big Bang, the high-risk system-wide cutover. A phased approach allows a hospital to stabilize a single function, like pharmacy ordering, before rolling out complex inpatient records. Leadership must also choose a turnover strategy, parallel processing or straight turnover. Parallel processing runs the old and new systems simultaneously for a set period. It provides a significant safety net but doubles the labor requirements. Straight turnover is more cost-effective but creates a total dependency on the new system the moment it is activated. The final go-live decision is a calculus that weighs the cost of redundant labor against the risk of operational failure. System implementation continues beyond the initial launch, evolving into a cycle of immediate support, performance evaluation, and long-term maintenance. To maintain stability during future upgrades, information technology departments utilize environment isolation. The live production environment contains active patient data. The test environment, or sandbox, is an exact duplicate where changes can be made safely. Protocols require every software update be validated in the sandbox before deployment to the live production system. A successful system implementation is an ongoing orchestration of data integrity, human adaptation, and continuous verification.